All right, so in Module 8, I'm going to be talking a little bit more about data analysis and some of the assumptions that need to be met before we can do an accurate amount of data analysis. So I'm going to be talking about independence of observation, autocorrelation, and some visual analysis that we'll be doing. So back to this big picture here in practice evaluation, as we moved on from goals, measurement, or design, and on to analysis. So some of the basic assumptions are independence of observation and how we're going to test for autocorrelation. So what do I mean by statistical assumptions? So with these assumptions, we need to make sure that our data is normally distributed and that there's no violations of any of the statistical assumptions that we would need to meet prior to moving into any kind of analysis. So what do I mean by normal distribution? I'm sure you've all seen the bell curve before. This is a perfectly distributed bell curve that's not skewed negatively or positively. You can see that each one of the standard deviations is exactly the same from the center or the mean. This might be a good illustration of standard deviation of IQ of the whole population, where we could see that 68.2% of the population is within one standard deviation of the mean, and then there are 0.22% that are two standard deviations are higher above or below the mean. And now I'd like for you to watch kind of like a video that illustrates normal distribution and what it is and what it isn't. Okay, so now let's talk about some data that's not normally distributed and what we can do with that. So in the following vignette, I'll just show you an example of individuals with cocaine dependence who are receiving an active medication versus individuals with cocaine dependence who are receiving a placebo. So in this axis, or in this graph, you can see on the horizontal axis is the number of days abstinent, and the vertical axis is number of individuals involved in the study. So if we're looking at the results of this study, we could see that this is pretty normally distributed. it looks like the average number of people made it about 90 days abstinent from cocaine use. There's a few people on the far positively skewed end that remained abstinent several months down the line. And then there's a few people who barely made it without relapsing. We could assume that probably some of those people received the placebo medication. So we could probably look at this and say, yeah, we've met our assumption of normal distribution here. And I think that we can go ahead and do a t-test, or a two-sided t-test, to see if there was a statistically significant difference between our placebo group and our active medication group. So let's compare that to this graph. This is looking at number of participants in the study and frequency of drinking on the job. So we could assume that this is probably a population with a alcohol use disorder. What do you think? Is this one normally distributed or not? As opposed to this one, which is pretty normally distributed. I would say that this one is positively skewed, and we can see that there's a lot of people that had 2 days drinking on the job, and a smaller number of people who had 8 days drinking on the job, which is probably a good thing. But since this is positively skewed, we would probably need to do some kind of transformation statistically in order to make sure that we met the assumption of normal distribution. So all is not lost. We would just need to transform the data statistically in order to make sure that we can run our test accurately. Another thing worth pointing out with this graph is it looks like all the people that had 0 days were excluded from the study. So that would almost certainly lead to a positive skew here. And that could just be related to the people that were excluded from the study, or the sample that was gathered for this particular study that was being used. So another one of the assumptions is independence. And independence means that one data point isn't impacted by another data point. What if we didn't have independence of observations? You could think of back to the cocaine example. What if one person's use was dependent on another person's use? So maybe somebody with the placebo group lived with somebody who was in the active medication group. Or if you've ever seen the movie Dallas Buyers Club, where they were testing the effectiveness of HIV medication versus a placebo. But it turned out within the study that people were mixing their medications, so at least everybody in the group would get half of the active medication. And then that kind of threw off the results because there wasn't independence of observations. The observations were dependent on one another because people were mixing their drugs. So that would mean that the basic assumption that each observation was independent and they weren't related to each other was not met. And that would obviously bias our data, and we'd have more noise in the data that would make it more difficult to analyze. Another issue in single system design is dependence, where one observation can be predicted from another observation, which is also known as autocorrelation. So a correlation of adjacent observations within a series of observations. So if those patterns become too predictable and repetitive, then we need to make certain statistical modifications in order to get rid of the autocorrelation. So let me break that down a little bit more. Here we can see an example that's clearly autocorrelated. So we could see that every other day this person has unhealthy meals, and it's a very predictable pattern. Maybe one day they're working from home and the next day they're working on the road. And we have this very obvious zigzag pattern that's very clearly autocorrelated. So what we would need to do in this situation is take a moving average, because if we ran a test or a t-test for statistical significance, everything's going to kind of fall apart and we're going to get very misleading information, because you can see that the variance here is in such a predictable pattern and each observation is dependent on the other. So again, autocorrelation is a correlation of adjacent observations within a single system design within a series of observations made over time. And without running a transformation, your data is going to give you kind of misleading results. Like you may think that you've got a statistically significant result, but realistically the autocorrelation is going to be a violation of statistical assumptions that we need to be able to prove out independence of observations to run the t-test. So later in the videos, when I show you the methods used to get rid of autocorrelation, we'll discuss something like a moving average. So in order to smooth out that zigzag pattern where each of the adjacent observations are dependent on each other, a moving average will help us to get an idea of the average baseline and the average intervention so that we can run a t-test that's going to meet these assumptions and give us accurate, valid results. So again, that moving average calculates the mean of adjacent pairs of data points and will transform our kind of messy data, maybe something that looks like this, where we can see a clear up and down pattern. So this might be an example of number of child outbursts per day. We could imagine maybe a scenario where a child's going back and forth between parents, and with one parent there's 2 outbursts a day, with another parent there's 4 outbursts a day, and there's a clear autocorrelated pattern. And a moving average can help us to smooth that out so that we can run our statistical, and a moving average can kind of help us to smooth that out so that we can get a average of what was expected during the baseline phase so that we can run a smooth comparison of a baseline phase to an intervention phase without worrying about any violations of statistical assumptions. And just worth noting, we're going to be doing some tests for autocorrelation and statistical significance. And I've had a few people in the past confuse the two terms. So when we're running a test for autocorrelation, we're just seeing if the statistical assumption of independence of observations is met, versus a t-test is looking at whether or not there's a statistically significant change from the baseline to the intervention phase. And so you need to run a test of autocorrelation before you can run a t-test. And if there is a statistically significant change within the t-test, then you would need to follow that up with an effect size to see the strength of that change.